All right, so nice. So send the document already, so you all can go through it. So you'll just be going through nodal analysis today. So y'all may have done it. Y'all would have done it before, right? So for those who understood it, as I recap, for those who didn't, I hope this lecture helped you all understand it a little better, right? So basically what nodal analysis is basically breaking down the circuit into nodes, which is the first thing you're gonna do. And with those nodes in the circuit, you could use those things to calculate currents and voltages. Because at the end of the day, those are the two things you want in the circuit. You want the voltage at this point, you want the current at this point. That's really what you're gonna boil down to. All right, and as I said before, to get those voltages and currents, it all depends on what the circuit give you, basically. It all depends on what in the circuit. All right, so the two techniques you could use to get those currents and voltages is called nodal analysis or loop analysis. This here is nodal analysis. All right, so basically, the first thing you need to do is label nodes. That's literally the whole consensus, the technique. You need nodes. All right, so before I start, these are the steps within the notes. So you need to go through these steps, and I'll go through them with you. Anytime you look at a circuit, all right, these are the steps you'll go through. But I want you all to remember this. When you have a circuit, and after you label your nodes and stuff, you may be thinking, all right, I have nodal, I have loop. Which one I gonna use when? I could use anyone when? Yes, technically you could use anyone anytime, but one technical work it out faster than the other one. So the rule is, and you can write this down. After you label it, and when you do loop analysis, you'll appreciate this more. If you have more loops, so if you have more loops than nodes, yeah, you use nodal. Use nodal analysis. It basically you use anyone they have the least of. So if you have less nodes than loops, you use nodal. The other way around is true, right? If you have more nodes than loops, you use loop analysis. Yeah, you just get through the question faster. You could use anyone, you get the same answers, but it's just one will be more efficient than the other one. All right, so if you have more, sorry, not say it like that. If you have less loops, use loop analysis. If you have less nodes compared to loops, you use nodal analysis. All right, well, for this lecture, we just use a nodal, but let's remember this, that is something real cool to remember. So when you're given a question, instead of picking the one that will take less time, you will know, all right, I draw my nodes, you can draw your loops. When you do loop analysis, you'll see what I mean by loops. If you know what it is already, you can probably catch it already. If you have less loops than nodes, you use loop analysis. If you have less nodes than loop, you use nodal. Very simple. All right, so that out of the way. So let's look to start with the steps. So the first thing you need to know anytime you look at a circuit is where is the ground? Where is the ground? So you know the symbol for ground is this, right? Or something looking like that. We need to know what node the ground is connected to. I repeat, you need to know what node the ground is connected to. Why? Because the voltage of the ground node is 0. You know what the voltage of the ground node is. And that will come in very handy in questions because that is one node that you actually know the voltage from. So the first thing you look at the circuit, you draw your nodes like we do last week. Nice. Second thing is you need to look for where the ground is. In the exam, so will most likely give you where the ground is. Yeah, if it doesn't, you could place the ground wherever you want it to be. But most of the time, he will give you where the ground is. So make sure and look for that little symbol. That's when you draw a little node. Wherever node the ground connected to, the voltage of that entire node, the endpoint wherever that node connected to is, the entire node is 0. Yeah, so just remember that. Second thing, well, you know you're drawing your nodes, you label them, so you know you label your nodes VA, VB, and all them stuff, right? Because the node is a voltage. So when you label it, you put VA and VB, right? Or you can say A, B, C, whatever one you want, right? But when you're doing these things, when you're labeling the nodes, you need to keep an eye out for something called supernodes. You need to literally keep your eye out for it. Because this could be the tricks, and this could cause you to lose marks in your exam, right? Because remember, for your exam, I don't know if you know this, Sir doesn't want you to actually get the values. He just wants you to break it down into the relevant nodal equations, and that is it. You don't need to solve for anything. Any assignments, yes, you actually have to solve for them, all right? But you can use multisim to do that. But in the exam, you just have to break it down into the nodal equations and you stop and write it. You don't need to solve anything. All right, so that is why, as he said, if you make a mistake in one part, you get the whole thing wrong. Because he's looking for a system of equations. And in order for that system of equations to be correct, all the equations must be correct. If one equation wrong, that means the entire system wrong. So you have to be very careful. And you have to have a keen eye when you're doing these things. Hence the reason why I break it down into steps. All right, so look for the ground, label your nodes. Keep an eye out for the supernode. You have to look for the supernode. So, continue. A supernode. What the hell is a supernode? A supernode is when you have a voltage source in between two unknown nodes. All right, so if I had something like this, let me try to face it. I have a resistor, say I had a battery. I hope everybody know what a battery is. So say I have this. So obviously when I draw my nodes, this here will be a node. All right, and then in between components, you have a node here. Let's call it VA. And you have a node here. Let's call it VB. So you'll notice that you are accustomed, and literally when you're accustomed doing it, you're accustomed with having a resistor here, you're accustomed with it being like this. But you notice there's a voltage source in between two nodes that you don't know the voltages for. You really don't know the voltage of it. Yeah? So anytime you have a voltage source in between two unknown nodes, literally looking like this, seeing that? Look at it. Put it in your brain, you have a voltage source, and you have literally two nodes to count it at the ends. Anytime you have this occurring in a circuit, whether it's a dependent source or independent source, which we'll get to just now, once it's a voltage source and you have two nodes at the end, this is a supernode occurrence. And you have to treat with this very specifically and specially. Yeah, so it's a different way of calculating these nodal equations when you have a supernode. And it's very simple. All right, but just keep your eye out for it. So you need to know, all right, wow, that is a supernode there. And I'll show you what to do when you actually see the supernode. But just keep your eye out for it. All right, so I'm training your brain to look out for certain stuff in your circuit. All right, so you went through, where's the ground? You know where the ground is. The node is 0. Draw your nodes. Look out for your supernodes. The third thing, as you see when you do an example, you need to decide whether the currents are leaving the node or entering the node, which we'll see when you do a question, all right? So let's take it for now. So in the fourth step, you analyze the circuit for the nodes that we know the voltage for. This will come in handy. This and number one is kind of similar. You need to analyze the circuit to look for nodes that we know the voltage for. Example, the node right after the battery, we know the voltage of that. Yeah, think about it. If we know the battery, so let me try it off here. So you have, say you have a battery, a resistor. Come back around to there. The ground is here, the ground there. So if I draw my nodes, I have a node here. And this whole thing here is a node. And since that is ground, the voltage at this node is 0. Yeah? So this node here, say the voltage of the battery was 5 volts, right? The voltage of this node here will be 5 volts because it's the voltage of the battery. Because this is a node right after the battery. In order for our voltage to drop, you need to go through a resistor or a component or something like that. All right, but if it's just wire straight up to the first resistor or the first component, the voltage at that node is always the voltage of the battery. Yeah, so that is the importance of step 4. You need to analyze the circuit for nodes that we know the voltage for. And you can remember from the tutorial, Sir didn't just give you one voltage source. He gave you different voltage source all over the circuit. So the node right after the battery, you know what is the voltage in between the battery and the first component, but as a resistor, well, you know that voltage. You know that node. All right, and you need to look out for, there's only mostly like two. So the node after the battery and the node that the ground connected to. Yeah, anything else, you have to look out for. All right, so that's step 4, look out. Step 5, you perform the nodal analysis for the equation. So how does go for the unknown nodes, obviously? Each node has a equation for it. Yeah, so that's what you mean by the nodal equations, which will form the system of equation. Each node that you don't know the voltage for have an equation. Yeah, you call it a nodal equation. All right, and we'll learn how to get that. Step 6, something called dependent sources. All are dependent sources, if you ever saw it before, it does look like a diamond, like this. It looks like a circle. It can either have an arrow, which means there's a dependent current source, or it can look like this with a battery. So it'll be a dependent voltage source. Yeah, so just remember that. All these things do, it does provide a voltage, a constant voltage or current, and these voltages or currents depends on somewhere else in the circuit. It depends on some voltage drop across a certain resistor somewhere else in the circuit. It depends on something. So it might depend on some current somewhere else in the circuit. It's dependent on something. All right, that's why they call them a dependent source. A battery, a normal battery, it doesn't depend on anything. That pushing up 9 volts no matter what. Yeah, but the dependent sources, it depends on something somewhere else in the circuit. All right, so just remember that if you see the diamond, there's a dependent, and when you look inside, if you see an arrow, there's a current source, and if you see, well, a normal battery plus and minus, there's a dependent voltage source. All right, we'll get into this more in depth as we continue in the lecture. All right, and the last step, we solve if needed. Keyword if needed. You need to use matrices. All right, this step here, you will not need to do it for your exam, so I really don't need to go through it that in depth. Um, you will not need to use it again really, in terms of actually calculating the voltages. Your second assignment, you will need to use your third one now, your fourth one definitely, the AC analysis. Um, so only the first one you really need to use it for. But you could use multi-simple. But yeah, but your final exam, you don't need to do step 7. You don't need to solve for them. You just wait to get the equations. So you don't need to have to pay too much with it. All right, so those are the steps. Look at them. Ground, your node, the label it supernode, and every 3 steps. All right, so I continue. Check the chat. Any questions? Make a stop if you all have any questions. Huh? All right, so I continue. All right, so other notes. Let's erase this. The voltage drop across the resistor is negative. Remember when we did the analogy? The voltage of the battery is like water, and the resistor is like a real thirsty brethren. When you go through that brethren, your water gonna drop. AKA, you gonna get less water in your tank. Yeah, so the voltage drop across a battery, sorry, the voltage drop across a resistor or any component, it will use voltage from the battery, it will use energy from the source. So that used energy is negative because you can't plus energy going through something, you will minus energy going through something because you're using up that energy. So the voltage drop across a resistor is negative. Keep that in the back of your mind, right? And the most important thing you will ever hear in this course, polarities. Make sure you know the polarities of stuff. If something going from 0 to 10 is a voltage rise. If something going from 10 to 2 is a voltage drop. Yeah, and that makes sense. If this was a battery and this was a resistor and this was a node after, you understand that the resistor will use energy. So obviously the energy after the resistor will be less than the energy before. So therefore you have a voltage drop. The voltage cannot rise going through a resistor. That doesn't make logical sense. Yeah? You don't get more food when you take out food from any pot. It really work like that. You get more food you take out from the pot, you get less food in the pot. Yeah? If it only used to work like that when you make macaroni painting for Christmas, you'll always have food you need because it will never finish. Actually, you'll get more and more and more and more. You'll have too much. All right? So let's remember these two things. It's very important. And the last thing on this slide, if you assume the currents, and this is very important, that's good. I think it's an equation you need to remember. All right, nice. So remember this, if you had to write it down, write it down. This is the most important thing you here, because this will help you to get the nodal equations. If you assume the currents are leaving or entering, leaving or entering. So if I have a node, let me see if I can help you. So let's say we have a node here, right? A dummy node. All right, so say we have this and this. A resistor here, a resistor here, and a resistor here. Yeah. So in this node, say we name this node VA. Yeah, we name it VA, right? We could either assume the currents leaving the node or we could assume it entering the node. So right here at the endpoint, we could either assume the currents leaving or entering. So I like to do it leaving, but it doesn't really matter what direction you do it. So if it's leaving, this is where you have to remember here. That's really important. Is the node we are coming from, subtract the node we are going to, divided by the resistor between them. Yeah? So let's draw something else. So if we extend this here, all right, and say this node here is VC. And let's say this ground. And we know the voltage of ground is 0. All right? So that ground there. So if we wanted to get the nodal equation, very simply, we got this node here. We got another node here. So like you say that node is VD. All right, so we have the node, we have resistors in between them, and we have nodes on the next side. We have no super node here. Notice that? So there's a normal nodal analysis. So if I have to get monodal equations for VA alone, it will look like this. So I'll say VA, and we get. All right, so the first thing, you only have one here, two, here are three entrances or exits, depending on how you leave it. So if I using the same equation here, the node we are coming from, since my voltage, my current going out, they will always come from VA. All right, so all my equations going to start with VA. So what shall we go? So I have VA. So the first one, let me start with 1 here. So I coming from VA and I go into VD. Yeah, that's what we'll go into the resistor. Yeah, so the equation will be VA, the node I coming from, subtract the node I go into, which is VD. All on the resistor between them. If that was say R1, it was R. Yeah, that is 1. So that one curve, that done. Now we have to do for 2 and 3. So 2 now, same thing. Plus the node we coming from, VA, subtract the node we go into, which is VC. All over the resistor in between them, let's say there's R2 over R2. The next one, 3, same thing. The node we coming from, which is VA, so we plus VA, minus the node we go into, which is 0. I divide it by, well, you say that's R3. Yeah, well, is equal to 0. Yeah, so this is the nodal equation for note to self, and remember this, very important. If you leave out this equal to 0 parts, you will get the entire thing wrong. Yeah, because I don't think I told you, there's something called Kirchhoff's voltage law. The sum of voltages or the sum of currents going into a node, all of them had to add up to 0. So think about it. This is V and R. Remember, V is equal to IR, right? So if I transpose this, I would equal to V on R, which is basically what you have here. So the sum of the current, so if this was I1, this was I2, and this was I3. I know you're not seeing it, but I3. If you add up all the currents, you're supposed to get 0. Because the current entering a node or entering a point, the sum of them must equal to 0. Or in a normal term, the sum of the current going in must equal to the sum of the current going out. So that is why you must put this equal to 0 part at the end. If you leave this out, it's no longer an equation, it's an expression. Remember from maths, if you don't have an equal sign, it's an expression. If you have an equal sign, it's an equation. It's a nodal equation, so it must have an equal sign. And it will always equal to 0. All right? So that's how that's works. If I had, let's say, switch it to going in, all that will happen is now I ending at BE. So if I doing it for this one, for the first one, the node we coming from. Now the node we coming from for this one will be VD. So that'll be VD subtract VE. The node we coming from minus the node we going to. Yeah? Over the resistor in between them. Plus, same thing for R2, the node we coming from, subtract the node we going to, which will be VE. All on R2 plus the last one, the node we coming from, which will be 0. Node we going to, all on R3. Alright, so it all depends on what you choose. Personally, I like to assume it going out, so I could just start with whatever my node is, my reference node is, but it all depends on what you choose. Whatever you choose, keep it constant. So don't be like for one node you're going out, and the next one you're going in, and you gotta keep it constant. You gotta use the same thing for all the nodes in the circuit. Okay, if you change it up too much, you will get the wrong answer. So you gotta assume everything going in if you're assuming that, or you assume everything going out. Yeah, you just have to be careful, right? So that's the importance. This here is basically the analysis here to get the equations.